calculus. All right, hopefully you did well on your test. Haven't marked them yet. I'm going to mark them what would be today, which would be Tuesday. My plan is to get those marked today. In the meantime, you had homework that I gave way back on Thursday. It's due by basically midnight on Monday. I'm recording this about 8 o'clock on Monday night. I've only received feedback on this from one person who said it did not go well for them. If there's more and I need to do a video on it, then I will. I may answer some questions about it though, just by virtue of what we're going to do today, because it sort of builds on it. So what we did on Thursday was we talked about increasing functions and decreasing functions, and a graph can be doing both, because this graph is increasing here and then it switches and it's decreasing here. And so what we did in order to figure out where does that happen, we took the equation that was given to us, or you should have taken the equation that was given to you, find the derivative, make the derivative equal to 0, and solve. Whatever number you get, or numbers that you get when you solve, those are test points. You check below those numbers and above those numbers to figure out, so if, let's say, this was 4, okay, then I would pick a number before 4, say like 1. I'd put it back into the derivative equation, not the original, but into the derivative equation. If I got a positive answer, it would mean that the graph is increasing, and if I got a negative answer, it would mean that the graph was decreasing in those sections. All right, when a graph changes from increasing to decreasing or decreasing to increasing, you create, for lack of a better word, I'm going to get a better word in a minute, but for lack of a better word for right now, you get a hill, at the top of a hill, or you get a valley. So if you had a graph that did something like this, okay, and I'm actually looking on page 320, and there's no math there. It's just, they're going to talk about some terms, so I'm going to talk about some terms, all right? So right now the graph is increasing, then it switches to decreasing, then it switches back to increasing, then it goes back to decreasing again. Where it switches from increasing to decreasing, we end up at the top of a hill. And where it goes from decreasing to increasing, we have what I would call a valley. Now, rather than calling them hills and valleys, they actually call the top of a hill a local maximum. It is a place where the graph reaches a peak and on both sides goes down on either side. So this is the top of a hill. I could slide down the hill on this side, or I could slide down the hill on that side. So that is a local maximum. Again, right here would be another local maximum, because you go downhill on either side, right? Here, this is a valley called a local minimum. It's called local because it's not, the graph could go lower, like the graph goes lower over here. And again, local max, the graph goes higher over here. But compared to the points just near it, this is a maximum value. All right. There are also sometimes, not all the time, but there are also sometimes what we call absolute maximums and absolute minimums. An absolute absolute maximum or minimum is a place where it is the highest or the lowest that the graph goes, period. So on this graph, this point, which is a local maximum, would also be an absolute maximum because the graph never goes higher than that point right there. So not only is it a local maximum, but it's also an absolute maximum. This point down here is an absolute minimum because it is the absolute lowest that the graph goes. It is not a local minimum because it doesn't go up on both sides. From this point it goes up this way, but it doesn't go up on this side, it just stops. So in order for it to be a local, it has to change, it has to go, for a minimum, it has to go up on both sides for it to be a minimum. If it just stops, okay, that's an absolute minimum. So this is a local minimum, but this is an absolute minimum. Now, sometimes a graph might not have an absolute maximum or an absolute minimum. So for example, if rather than it stopping, if it had an arrow and it said it kept on going down forever and ever and ever, then there is no absolute minimum because there is no absolute lowest the graph goes. It goes down forever. So there doesn't have to be an absolute maximum or an absolute minimum. Local maximums and local minimums are often called local extreme values or local extrema. That's at the bottom of 320 if you want to read that paragraph, okay? Sometimes they call them turning points because it's where the graph turns and changes direction. So, in example number 1, on, I can't see, on page 321, example number 1, I'm just reading my notes. I think I'm just going to do, okay. It doesn't talk about me doing, okay. So in example number 1, they give you a graph. And again, I'm just going to give a rough sketch of it. They have like specific points on page 321, top of it. And it goes something like this. And then it kind of goes up, makes a point, and then kind of goes down like that. Okay, it's not very good, but that's what it does. All right. Now, it says determine the local and absolute extrema for each function. So we're looking for local maximums, we're looking for absolute maximums, we're looking for local minimums, and we're looking for absolute minimums. So let's look for local maximums first. There would be one here, wherever here is. And according to the picture, again, I'm just looking at the picture, and I'm cheating, I'm looking at the answer. But if you look at the graph on page 321, it's at 3 and 9. So this is over 3, 1, 2, 3, and up 9, okay? So I have a local maximum at 3 and 9, and it looks to me like I have another maximum here because it's going up and then it's going down. It doesn't matter that it's in a point, it's still doing that. And they say that is at 10 and 7, across 10 and up 7. So I have another local max at 10 and 7. Now what about the absolute maximum? Is there one? And if so, where is it? This is where, if we were in class, I'd be getting you to answer me. However, this is the absolute maximum. That is the absolute highest that the graph goes. So the absolute max is at 3 and 9. Now we have to look for local minimums. I really only see one. I only see one local minimum, just this one, because it's the only valley that I see. This is not a local minimum because it doesn't go back up on the other side. So where is that? According to them, they say that is at 6 and 5. So over 6, up 5. Now, what about absolute minimums? That is not the absolute lowest that the graph goes. That is. So what is that? That is actually sorry, I'm looking at the wrong one. The absolute minimum is at 10, 11, 12, and 1. The absolute is at 12 and 1. Okay, so the absolute minimum value, the lowest that it goes is 1, and it happens when the x value is at 12. In the text, they just give the absolute minimum as 1, but I give it as a full location. It's across 12 and up 1. Doesn't matter either way. I don't care how you do that. They do the same thing for part B. The graph they give for that one looks like this. Comes down, goes up, and goes back up. Okay, and it ends at either end. So again, local maximums. There's only one of them. It's right here. Whereas right here looks like 0 and 4 to me. So I have a local maximum at 0 and 4. Absolute maximum, though, is up here. That is the absolute highest that the graph goes. And so the absolute is 4 and 12. All right, local minimums. I see 2 of them. I hope you do too. There's one here and there's one here. So where are those points? They are at -2 and 0 and +2 and 0. Absolute minimums. Absolute minimums are actually the same. Those 2 points are the places where it is absolutely the lowest that it goes. So there's actually 2 absolute minimums for that. So a place where you have a local maximum, at a local maximum, your graph changes from increasing to being decreasing. That is called a critical point, okay? It is called a critical point. A critical point happens when the derivative is equal to 0, and we did that in the last section. In order to find those test points, which they're now calling critical points, in order to find those test points, you found the derivative and made it equal to 0. Another critical point could be if the derivative doesn't exist at that point, but we don't see that very often, so don't worry about that. So this idea that critical numbers, critical points happen, that local minimums and local maximum happen at critical points. And so this would also be a critical point. It is a place where the graph changes direction. Those are critical points. So the idea that a graph changes direction, it has a local maximum or a local minimum at a critical point, that is actually something called Fermat's theorem. It's so universally known that it's a theorem. All right, don't worry about that. That's just, if you ever hear the term Fermat's theorem, you know it, okay? You do know it. It is just that critical points create local maximums and local minimums. That's all that that is. All right. So I want to look at example number 2. And I think that's all I'm going to do. I'm just going to go over example number 2. And then I will leave example 3 and 4 for Wednesday. Again, if you are struggling with any of the homework, either from 6.1 or this, please let me know so that I know whether I need to make a homework video or not. So in example 2, it talks about how do I determine where that local extrema, where those critical points are, where are those local maximums and local minimums. How do I figure that out without having to draw the graph? So it says determine local maximums and local minimum values for the function f at x. So f at x, and remember f at x just means y, is x cubed minus 3x plus 2. So the first thing I have to do is I have to figure out where is the graph increasing and where is it decreasing. So if you told me that you were struggling, or you didn't tell me but you are struggling with section 6.1, again, this is what we do. These are the steps every single time to figure out if something is increasing or decreasing. Step number 1, find the derivative. So the derivative would be 3x squared minus 3. Step 2, make the derivative equal to 0. So 0 is equal to 3x squared minus 3. Step 3, solve. So 3 is equal to 3x squared. I'm going to divide both sides by 3. So x squared is 1. So x is equal to plus or minus 1. So step 1, find the derivative. Step 2, make it equal to 0. Step 3, solve. Step 4, create intervals. These are my critical points. These are places where I could potentially have local maximums or local minimums. So how do I know whether they're maximums or minimums, or whether they're faking me out? Because sometimes it isn't really one. So -1 is a critical point, +1 is a critical point. Think of this as a number line. Think of this as a number line. I'm going to pick a number before -1. Anything you want, doesn't matter. Just needs to be lower than -1. So I'm going to, go way out on a limb and go -2. Take that number, put it into the derivative. Do not put it back into the original. Put it into the derivative. So if I take -2 and I do 3 times -2 squared minus 3, do I end up with a positive number, or do I end up with a negative number? Will I end up with 4 times 3 is 12. 12 take away 3 is 9. So I end up with a positive number, which means from anything before -1, the graph is increasing. So if I had a graph and I had -1, anything before -1, the graph's going up. So now I'm going to check between -1 and 1. Any number I want, as long as it's between -1 and 1. I can pick -0.5437 if I want, but I'm going to choose 0 because that's between -1 and 1. I'm going to put it into the derivative. So 3 times 0 squared minus 3. So that's 0, take away 3. So my answer is -3, so my answer is negative. So now the graph is decreasing. So even if I just draw it here, what do I end up with? I end up with a local maximum. So this is going to be a local maximum. There's a local maximum at -1. I already know that. And then I have to check after 1 because I need to know, is this graph going to change direction again and go up? Because if it does, then I have a local minimum here. If it just continues downward the whole way, then that's not a local minimum. So I need to find out what I have. So I'm going to pick a number bigger than 1, any number I want. Go and pick 2. So 3 times 2 squared minus 3. Again, put it into the derivative. So 2 squared is 4 times 3 is 12. 12 take away 3 is positive 9, which means the graph is going up. So again, I have a local minimum. Okay, so I have a local maximum at -1 and a local minimum at 1. So really my graph looks like this. Now I can even give them the points because it says determine the local maximum values and minimum values. So if I'm going to determine the local maximum, I know it's at -1, but what is the maximum? How high does it go? What I really need is I need a y value. So if I need a y value, I'm not going to go back to the y prime formula. I'm going to go back to the y formula because I need a y. I know that I have a maximum when x is -1, but what is that maximum? How high does it go? Well, I don't know. I'm going to put it in here. -1 cubed is -1. -3 times -1 is positive 3. So I have -1 plus 3 plus 2. So that is 4. So I have a local maximum at -1 and 1, 2, 3, 4. I have a local maximum. So I know it goes up and then it changes direction. Okay. Now I have a local minimum at 1. But what is that minimum value? How low does it go? So again, I want a y value. So I don't go back to the y prime formula. I don't go back to the derivative formula. I go back up here. So 1 cubed is 1. -3 times 1 is -3 plus 2. So 1 take away 3 is -2 plus 2 is 0. So at 1, the minimum value happens at 0. So I can now give a pretty good picture of what that graph looks like. And I didn't have to do a table of values. All I had to do was find the derivative, make it equal to 0, and I could tell them where it was increasing, where it was decreasing, and where the maximum and minimum values happened. I'm not going to give you any more than that today. I think this video is long enough for you to watch. So I'm not going to do any more than that today, but tomorrow I will go over examples 3 and 4. I will give you just a few questions to do today, and then I'll give you just a few questions to do tomorrow. Again, if you're still struggling with section 6.1, it's very, very similar to this, just without finding these points, but everything else about it is the same, okay? So maybe, hopefully, I've answered some questions with that. So if not, let me know. All right, talk to you again, and I hope to have your marks by the end of day on Tuesday. I'm hoping, unless, you know, life explodes. Well, hello, Autumn. Do you want to come and say hi? Come here. Autumn wants to say hi. See? There's Autumn. She says hi. Yes, 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 hello. Yes, hello, hi. All right, so we'll talk to you again, and yeah, so hopefully that goes okay for you.